In the previous lecture, we completed introduction to power system, and now in this presentation, we will try to understand working of AC power supply system. I will explain how AC power is transmitted or supplied from the generating end to the load end. This end here is the generating end. You can see a thermal power plant at this end, and power generated at this end is transmitted following this path to the load end. So this end here is the load end, and in this particular case I am taking a society or locality as the load. There are various houses acting as the load. Loads are of different types. You can have industry as a load, or college or hospital or market, but for this case we have taken a society or locality as the load. Generating end is the source end. We can simply call generating end as the source end because this end is the source of electrical energy. We are burning coal to produce the electricity, so this is the source, and these houses are the load. Now the first question comes in our mind is why we need to transmit the AC power over this long distance. Why can't we construct the power station near the load? This used to happen in the early days. We were having two options. The first option was to construct the power station near the load where the electricity is demanded, or we can construct the power station near the raw material. The raw material for thermal power plant is coal, and it is not important that all the loads are near the coal mine. Let's say this is the coal mine here, and for example the power plant is generating 2000 megawatt of power, and let's say 200 megawatt is consumed near this coal mine. There are people living near the coal mine, so 200 megawatt is consumed near the coal mine, and we are left with 1800 megawatt. So we need to transmit this 1800 megawatt to the regions where we don't have coal mines or we don't have rivers for hydro power plant. So this is the practical scenario when we are bound to transmit the power over a long distance. For example, the electricity generated in Bihar or Jharkhand, we transmit to Delhi. Delhi is the capital, it is the metro city, and the requirement of electricity is very high. So we need to transmit the power to Delhi. Not all will be transmitted to Delhi. For example, out of this 1800 megawatt, let's say 800 megawatt is consumed in the state itself, Jharkhand or Bihar, and remaining 1000 megawatt is transmitted to Delhi. This is simply a hypothetical scenario. I am not talking about the exact figures. This is a simple example to explain you why we need to transmit the AC power over a long distance. So we are constructing the power station near the coal. What if we construct the power station near the load? For example, we construct the power station in Delhi itself. There are few power plants in Delhi. For example, in Dadri we have power plant. It is not politically in Delhi, but it is for Delhi NCR loads. So let's try to understand what will happen if we construct the power plant near the load. In that scenario, you need to transport the coal over this long distance. Now you are transmitting the AC power over a long distance, but in case the power station is constructed near the load, you need to transport coal over this long distance. Now how you can transport the coal? You can transport the coal using the Indian Railways, of course, and the cost of transportation will be very high as compared to the cost of transmitting the AC power. The cost of transportation of coal will be higher because we need huge amount of coal to run the power plant. To meet the one-day demand, of the load, we need thousands of tons of coal, and to supply this much coal, we need to invest huge amount of money. So to cut the cost, to reduce the prices of electricity, we need to construct the power plant near the source, that is coal in case of thermal power plant. And this is the reason we need to construct the transmission lines, very long distance transmission lines, to transmit the electrical power. Now what about nuclear power plant and hydro power plant? Can we construct them near the load? We cannot construct a nuclear power plant near the load because we are producing the electricity from the nuclear fission process, and to perform the nuclear fission we require radioactive material. So we are dealing with radioactive material, and from safety point of view the nuclear power plant must be constructed away from the human population. So again we are required to transmit the AC power over a long distance. In case of hydropower plant, we need water, we need river or any other water source, and the dam must be constructed in hilly regions only. We need to hold the water, and to avoid the flooding situations we need hilly regions. So again we are having one constraint, and it is not important that all the loads are there in the hilly region. So again we are required to transmit the AC power over a long distance. So this is all for the need of transmission line, and now we will talk about other aspects of AC power supply system. We are producing electrical power using the generator, and let's say the voltage rating of generator is 11 kV. We can have generators having the voltage rating equal to 15 kV also, but for this particular case let's say the voltage is 11 kV. Now we will step up this voltage to a higher value of 400 kV. Again there is one question, why we are stepping up the voltage from 11 kV to 400 kV? We are stepping up voltage because we need to avoid the line losses. We are using these lines to transmit the power, and these lines we call as transmission lines, and they are made of aluminium and steel. Aluminium and steel will definitely have some resistance, and as current is flowing through this wire there will be I square R losses. Now if you increase the voltage from 11 kV to 400 kV, if you increase the voltage, the current will decrease. The current is decreasing because power is constant and power is equal to VI. So if you increase V, I will decrease to maintain the same power. So this is the reason we are stepping up the voltage from 11 kV to 400 kV. In India we have few lines having the voltage rating more than 400 kV. We have lines having the voltage rating equal to 700 kV, but for this we will consider the voltage rating to be 400 kV. So one thing we can point, along with generator we require a transformer which is acting as step up transformer. This particular transformer we call generator transformer. The generator transformer is same as the other power transformers, but the operation is different. In case of generator transformer it will always work as step up, but the power transformers can work as step up or step down. So there is a transformer known as generator transformer or generating transformer associated with generator every time to step up the voltage. Now we have stepped up the voltage, we will transmit it over a long distance, and as we require lower voltages at the load end, we need to step down the voltage as well. For this purpose we use substations. Substations are multi-purpose stations. We have transformers and other electrical equipments in substation. There are different roles performed by the substation, but for this example we will only assume that substation is stepping down the voltage. So from 400 kV we will step down the voltage to 220 kV. The primary side of the transformer is getting 400 kV and the secondary side of the transformer is giving us 220 kV. This 220 kV is again transmitted, and we will step down 220 kV further to 132 kV. 132 kV is transmitted and stepped down at other substation to a voltage level of 33 kV. 33 kV is stepped down to 11 kV, and 11 kilovolt is stepped down to 400 volt. So this is how the standard transmission voltages look like. These voltages are not random voltages, I have not taken them by my own, but these voltages we call as standard transmission voltages. Okay, now there is one important thing you must see in this diagram. Here we are having three-phase, three-wire system. Three-phase, three-wire system means we have three phases RYB, red, yellow, blue, and three wires are there. So I will write three-phase, three-wire system. Here also we are having three-phase, three-wire system. Three-phase, three-wire system again. Three-phase, three-wire system. Three-phase, three-wire system. Three-phase, three-wire system. And this one is the last three-phase, three-wire system. Here you can see one extra line, the yellow line. So this system is three-phase, four-wire system. This is three-phase, four-wire system. The fourth wire, the new wire, is neutral. The initial three ones are red, yellow, blue, and this one is the neutral. So we are having three-phase, four-wire system, and different houses are connected between Rn, Yn, or Bn. For example, this is your house, and this is your friend's house, and your house is connected between R and N. Your house is connected between R and neutral, and your friend's house is connected between yellow and neutral. It is connected between yellow and neutral. And what is the voltage you are getting at your house? What is the voltage you are getting? Here this transformer is stepping down the voltage to 400 volt, but you will say we get 230 volt in our house. This is true. You will not get 400 volt because 400 volt is the voltage between two different lines. I will try to explain this concept because it is important. We are having three lines. Red, yellow, and blue. And in the last system, we are having three-phase, four-wire line. So other line is there, which is the neutral. And if you calculate the voltage between R and Y, you will get 400 volt. If you calculate the voltage between yellow and blue, you will again get 400 volt. And between red and blue, you will get 400 volt. So all these voltages are line voltages, and you already know what is a line voltage. The voltage between two different lines is line voltage. Now we will find out the phase voltage. There is new term, phase voltage. Phase voltage is the voltage between any of these three lines and the neutral. For example, if you calculate the voltage between red and neutral, it will be equal to 400 volt divided by √3, which is equal to 230 volt. Because phase voltage, let's call it VPH, and line voltage VL is having the relation VPH equal to VL by √3. VL is equal to 400, so VPH will be 400 over √3, which is equal to 230 volt. Now look at here. Your house is connected between red and neutral, and between red and neutral, what is the voltage? It is equal to 230 volt. So your house will get 230 volt of voltage. And what about your friend's house? He will also get 230 volt because his house is connected between yellow and neutral. Yellow and neutral is also the phase voltage, which is equal to 230 volt. So both of you will get 230 volt in your house, and most of the appliances in our household is single phase load. I will write this down. Single phase load. By single phase load, I mean the loads like AC, television, fridge, washing machine, etc. are connected between one phase and neutral. The one phase may be red, yellow or blue, and this is neutral. So the load is connected between red and neutral, Y and neutral, blue or neutral. For example, in your house, your television is connected between red and neutral. So it is getting the voltage equal to 230 volt. But in industries, we may have three-phase load. And these three-phase loads are connected to the three phases of the line. The load will be connected to red as well as yellow as well as blue. This is the three-phase load connected to red, yellow and blue. Three-phase load. I hope the explanation is clear to you. Sometimes you will find there is no power at your home, but there is power at your friend's home. This is because your house is connected between red and neutral, and his house is connected between yellow and neutral. We are having fuses like this, and let's say this fuse, the red fuse, is blown up. So there will be no power at your house because the fuse is gone, but at your friend's house there will be power because this fuse is working. These are few things you must know. Now let us talk about transmission, distribution and generation. In this diagram, if I divide it, I will get the generation part before this line. This part is the generation part, and from here to here we have transmission part. I will write this down. This part is generation part. From here to here we have transmission part, and from here to the load we have distribution part. You can also divide transmission into two different parts, primary transmission and secondary transmission. The same thing you can do with distribution also, primary distribution and secondary distribution. But for now, it is important to understand which part is generation part, which part is transmission part, and which part is distribution part, because power system is all about generation, transmission and distribution. So this is all for this lecture. If you have any doubt, you may ask in the comment section. We will try to cover other basics of power system in the coming presentations.